Hello and welcome. In this video I'll be covering section 2.8, which is over related rates. So my goal for you by the end of the video is to be able to examine related variables as well as to be able to solve related rate problems. So what are related variables? Well, essentially if you have two or more variables that are related to one another, then what's nice is their rates of change with respect to a time t are also related. So as an example here, you can see if we had something where the two variables were related to each other, like y equals 4x, then their rates of change with respect to time, which would essentially be like taking the derivative with respect to t, would be equivalent to dy over dt equaling 4 times and then dx over dt. So again, notice here that the rates of change are still related to one another. And essentially what we're doing is we're just differentiating both sides of the equation with respect to t, which if we think about how implicit differentiation works, we have to use this idea of chain rule, and then we make the assumptions that both, in this case, the x and the y are actually differentiable functions of t, which then allows us to follow the chain rule and come up with that expression dy over dt equals 4 over dx dt. So let's go ahead and work through a quick example here. Notice here it's actually defining that x and y are differentiable functions of t. So even though we could have just assumed that was true, this one's explicitly defining it that way. And we have this relationship between them that's y equaling x cubed plus 2. So essentially what we want to do here is, as it says, it tells us a specific time when x equals 1, we know dx dt is equal to 3. So this is kind of a combo step right here. So if x is equal to 1, we know that dx dt must be 3. Then it wants us to find specifically dy dt, specifically when x is equal to that 1. So the first thing I would want to do is go ahead and just take the derivative of both sides with respect to t. So of this expression right here, so derivative of y with respect to t, that would just turn into dy over dt being equal to, and now I got x cubed, then I'm taking a derivative with respect to t, so that would turn into 3x squared just by power rule, but then times dx over dt because of chain rule. Again, this is a different variable that I'm taking with respect to than x, so just like implicit differentiation, we have to multiply by the dx over dt, and then the plus 2, its derivative would just turn into 0. So now at this point I should be able to plug in the values that they gave us. So to find dy over dt, when x equals 1, I'll just plug in 1 where I have x, and then times dx dt. Well, it's told me in the problem that dx dt had a value of 3 at that exact moment, so I'll just multiply by the 3. And at this point, it just turns into, let's simplify it, so dy over dt in this scenario is going to turn into 3 times 1 times 3, which really would just equal 9. And if they gave me units for this, which it did not provide units, I would go ahead and include those units on that 9 because, again, this is a rate. So it's possible that that could be something like inches per second or feet per minute or anything along those lines where it's just some unit of measurement but in a rate format, so per a unit time. Could be seconds, minutes, hours, whatever. But hopefully this kind of made sense how at the very beginning we're just taking the derivative with respect to t, and then we just plugged in the values that they gave us, the 1 and the 3, and then that allowed us to solve for the dy over dt that it was asking for. Now as far as our approach to these types of problems, hopefully this slide will help kind of give you a little bit more of a step-by-step idea here. But these are, again, just more guidelines, not so much you have to always do it in this order, but this is usually the order that you're going to go through and solve these related rate problems. So notice the first thing we want to do is identify everything that's given, as well as everything that I need to find out. So crazy enough, the first thing you do is read the problem and identify your key parts. If it's possible, if this happens to be something where you can actually draw a picture to represent the situation, sometimes that can help you reason through the process, but sometimes there really isn't a sketch that you could draw. So again, you don't always get to draw a picture, but if you feel like you can, or if there is some sort of context that allows you to draw it, using, say, like triangles or circles or anything along those lines. Anytime you're doing something geometry related, usually having a visual can help you identify the parts that you might need to solve for. After that, we need to go ahead and determine from whatever the problem gave us what the equation is that I'm actually going to use that will relate all of the variables that they provided for us. And then at that point, I should be able to identify what rates of change I need to actually figure out that are either given to us or they need to actually be found. But again, we just, at this point, relate the variables together, and then we follow that up with actually differentiating both sides. So again, differentiate both sides with respect to t. Key part there is I'm doing it with respect to this concept of time, hence the name rate. And I have to remember, anytime the variable is not a t, I have to use the chain rule concept. So if it was like a letter like, I guess, z, I'd have to multiply that. Once I've done the normal power rule or whatever I might need, I'd have to multiply by something like dz over dt. At this point, once we've taken the derivative, we do what we did on the last step for the previous example, which would be just plug in any of the numbers that I know for the values or rates of change, and then I would then solve for whatever is left. So it should usually, if you've done things correctly, turn into there's only one thing left that should be a rate of change, whether it's a dy over dt like the last example, or any other thing such as dx dt or dz dt or dv dt, any of those that have a rate of change that we need to solve for. Once I plug in the values, I should be able to isolate it. So let's go ahead and work through another example here. It says that we have air being pumped into a spherical balloon, so key word here being sphere, at the rate of 4 cubic inches per minute. So cubic inches, that's like a volume, and a per time, that should really be something like, if we wanted to define it as we're reading, that would be like the change in volume per change in time. So that 4 is equal to, or able to be plugged in everywhere I get dv over dt. Then it says to find the rate of change of the radius, so that would be dr dt, or the change in radius per change in time. And it gives us a specific value for the radius of 2 inches. So for this one, since it has this volume concept, I would need to use the volume for a sphere. So volume for this sphere, if you didn't know, you could do a search for it, or hopefully this is something that you recognize, it would be the 4/3 pi r cubed to come up with the volume of the sphere. So essentially what I do is I take that expression that related the variables, which is my volume formula, and I just take the derivative with respect to t, so that would turn the left side into dv over dt, equaling 4 pi thirds, that's all just a coefficient, so that would just stay 4 pi thirds. And then it would be times the derivative of r cubed. Well, r cubed should turn into 3r squared, but again, that's not the letter t, so I have to multiply by dr over dt. And so if I simplify, it looks like the 3's actually will get to reduce here, because 3 divided by 3 should turn into 1. So if I simplify this, my dv over dt formula, or equation, really just turned into what looks like 4 pi r squared times dr over dt. So at this point, I should be able to now plug in the numbers or the values that they gave us. So it did say that dv dt was this 4, so I can put 4 where dv dt is, equals 4 pi times r squared. Well, it said that the radius that we're going to deal with is this 2, so it'd be 2 squared, then times dr dt. Well, that's the thing I'm trying to solve for, so that's my unknown. So when it comes to trying to simplify this, all I'd have to do is just divide both sides by this value here. So I've got 2 squared is 4, times 4 would be 16. So really that's 16 pi that I would have to divide both sides by. If I could write 16. Now the 16 and the 4 look like they should be able to reduce to a 1 and a 4. So my dr dt for this specific problem is going to turn into what looks like 1 over 4 pi And this one did give us a unit. In this case, my radius would be measured in inches, it looks like. So this would be inches per unit time, which it said was minutes. So notice again with this one, what's a little bit different compared to the previous examples, this one actually had a context, so I did need to make sure I included whatever the units of measurement were. Let's move on to another example here. Notice this one is just telling us that we have a point that's moving along a graph. In this case, the graph being y equaling 1 over 1 plus x squared. Then it does give me this value for dx dt is 2 centimeters per minute. And it wants us to find dy over dt, specifically at two different values. So one time it's going to say when x equals -2, another time it's going to be when x equals +2. So the first thing I would need to do is just take the derivative with respect to t. For this one, I'm going to go ahead and just rewrite it using a negative exponent here just to make the derivative part a little bit easier. It is going to turn this into a little bit more of a chain rule idea, because there's now a function inside of another function. So with regard to taking a derivative with respect to t, I'd have dy over dt on the left side. On the right side, I would do the power rule, so -1 would have to come out front. 1 plus x squared would stay the same. Power drops by 1, but now I do times the derivative of the inside. Well, the derivative of the inside would turn into, looks like 0 plus 2x, which is just 2x, but again that's not the variable t, so I need to make sure I multiply by dx over dt. So if I can simplify, let's go ahead and do it. So we've got dy over dt is equal to, in this case it looks like I've got a -2x in the numerator, and then the denominator would turn into 1 plus x squared quantity squared. To make that power now positive, just dropping it to the bottom, but still times dx over dt. So at this point now I should be able to substitute in for our values. So with part A, it said I want x to equal -2. So if I plug in x equals -2, that gives me, for this one, I'll go ahead and change color a little bit, dy over dt being equal to -2 times the -2. So just plugging in that x value over 1 plus a -2 squared, quantity squared, then times the dx over dt, which they gave us in the problem as 2. So if I simplify everything out, it looks like I've got -2 times -2 times +2 in the numerator, so that would just turn into 8. And then on the bottom I have -2 squared, which would be 4, plus 1, which would be 5, and then that squared, which would turn into 25. So it looks like in this case the dy over dt when x is -2 would be this positive 8/25. Doesn't look like that reduces. And this does have a context to it, so we can go ahead and put, this would be centimeters per minute. Which again, that was just right here to let us know what the units were. So that would be my answer for when x is equal to -2. Now let's go ahead and try the next one, which is when x is equal to +2. We're not going to do a whole lot different, it's just a different number that we're plugging in. So dy over dt would be equivalent to -2 times now +2 over 1 plus 2 squared, quantity squared, then times dx dt, which again is another 2. So it looks like for this one, dy over dt, I've got one less negative on top this time. -2 times 2 times 2, that would actually come back -8. And then on the bottom, squaring 2 gives me 4, plus 1 is 5, and squaring that results 25. And again, the units still would be centimeters per minute. So I've got -8/25 centimeters per minute, apparently when x is equal to 2. So again, what this is doing is just think of it as if I were to graph the original function, this y equals 1 over 1 plus x squared, if I could just picture that there is a point that's moving horizontally in the positive direction at a rate of 2 centimeters per minute, I'd be figuring out how fast the y value is changing as I follow the graph at that speed. In this case, I got two different values depending on which x coordinate I was at, but it was able to come out relatively close to the same thing, just one positive and one negative. Does not always happen to work out that way. It's just kind of coincidence with this particular problem. Let's go ahead and do a couple more examples. This one now we've got a little bit more context going on. So we have a boat that's being pulled by a winch that happens to be on a dock. It says that the winch is 12 feet above the deck of the boat. So if I were to maybe start drawing a situation here that's got 12 feet above whatever the level of the deck of the boat would be. So if I said that we have the front of the boat being maybe this point right here, the rope then is attached to the top of this, so that would create this right triangle situation. So I'll get to use Pythagorean theorem potentially. And it says that the winch is pulling the rope at a rate of 4 feet per second. And then it says to find the speed of the boat when 13 feet of rope is out. So that would be when this is exactly 13. And we know that the direction here that we're going is going to be, it's reducing if I'm pulling in the rope. That should actually be like a negative 4 feet per second for whatever variable I wanted to call that. So if we just maybe went with A, B, and C, which are relatively common with a right triangle, we know that we'd have the relationship between those as a squared plus b squared equaling c squared. If I said to go ahead and solve or plug in the value, it seems like this 12 is going to be constant, but let's just go ahead and kind of keep that as is. Actually, let's plug it in. So with this one, it would be a squared plus 144, because 12 squared is 144, is equal to c squared. That way, when I do the derivative with respect to t, I'd end up with 2a times dA over dt. Then plus, well, the derivative of a constant would be 0, so plus 0 right there is equal to, and then now c squared with respect to t, that would turn into 2c times dc over dt. And so now if I were to take the values that they gave us, so we knew that the 12 was already a constant, so I've already dealt with the 12, don't need that anymore. It does say that I have this negative 4 feet per second. That seems like with how I've labeled this side, this value really is a dc over dt. And then it gives us this value right here, which is actually equal to c, so I should be able to plug that in. And then I do have this right triangle situation going on, so I could do 12 squared plus the a squared that I don't know should equal 13 squared. Just figure out what that specific a value is in this moment in time. So it would be 144 is equal to, or plus a squared is equal to 169. If I subtract the 144 over, that then gives me a value for a squared to equal, it looks like 25. And so if I square root that, that should give me an a value of 5. So I should be able to now plug that info into our expression over here. So I should be able to do 2 times the a that I just found times dA over dt, that's the part that I don't know, that's what I'm trying to solve for, is equal to 2 times the c value, which was 13, times the dc over dt, which was the negative 4. So if I were to now simplify everything, it looks like I've got 10 times dA over dt being equivalent to, if I multiply those out, let's see, that would be, what, 54 doubled, so negative 108. And then just divide the 10 away. I know that dA over dt would come back as, let's see if we can reduce that down to, I guess it was just divisible by 2 for the top and the bottom, so negative 54 over 5. And this was, as far as the unit was, it looks like it's feet per second. So feet per second, and since that came back negative, that means really all it's doing is it's just losing distance from whatever its current position is. So I'd have my dA over dt, it would be coming towards the dock at a rate of negative 54 feet every 5 seconds, essentially. And we'll do one last example here. This one now is going to be a little bit more of the business application. So notice we have the situation where it's giving us a cost and a revenue equation. So we've got our cost equation here as the C equaling 75,000 plus 1.05x, and then we have our revenue equation, which is 500x plus this x squared over 25. So it wants us to then figure out if we have a specific week, if the production in 1 week is specifically 5,000 toys. So again, x is the number of toys, so that would be the x that I'm going to get to replace. And it's increasing, so positive 250 toys per week. Well, that should then be my dx over dt, because again, the x variable is representing the number of toys. So if I know that 250 is dx over dt and 5,000 is equal to x, I should be able to, just by looking at the equations, do my derivatives with respect to t, and then plug in those values to be able to solve for, in this case, the rate at which the cost is changing is going to be dc over dt. And so if I derive that first one with respect to time, or t, that would be dc over dt being equal to, well, 75,000 is a constant, so that would turn into 0, and then plus the 1.05 times, well, that would turn into 1 essentially, but then times the derivative of that, which would be dx over dt. So if I go ahead and now plug in the dx over dt that they gave us, notice with this one there wasn't any x left to replace, so I don't have to plug in 5,000, it's just going to be 250. So the dc over dt at that moment in time is going to be whatever 1.05 times 250 is. And if we go ahead and figure out what that value is, looks like it comes out as 262.5. And if we think in terms of what is this now being represented as, well, it's the rate at which the cost is changing, so that should be dollars. And then per, in this case, it looks like the rate at which I would be going is a per week idea, so it would be per week. Knowing that it was dollars also lets me know what kind of rounding I should do. I can have partial dollars, I can have 0.5 or 50 cents, so I did not have to round that one. If we go ahead and do the same thing for my revenue expression, the derivative of r with respect to t would just turn into dr over dt, being equal to then 500x, and the derivative of that with respect to t would turn into 500 times dx over dt. Then plus, with this one, I could really just kind of separate out that 25 that you're dividing by and just consider that a coefficient of 1 over 25. But if I go ahead and take the derivative and have 2x over 25, then times the derivative of x with respect to t, so another dx over dt. So once again, I just plug in my values now to be able to solve for not my dc, but dr over dt. And in this case, it looks like it would turn into whatever 500 times my dx dt, which is that 250 they gave us, plus 2 times the x value they gave us, so that would be 5,000, goes in this spot, over 25, then times the dx dt, which is 250 once again. And now it just turns into a pressing buttons exercise, 500 times 250, added with 2 times 5,000, divided by 25, but then multiplied by 250. We probably could have reduced that before typing it in, but in this case, it wasn't that tough to type those numbers in. It came out as 225,000, and again, this would be dollars per and then week. So if we go to the last one, it says the rate at which the profit is changing, so I'll have to actually create the profit expression. Well, profit is equal to our revenue minus our cost. So for this one, my profit equation really would be the revenue, 500x plus x squared over 25, then minus the cost, which is going to be 75,000, and then I can distribute that negative through and actually say it's minus 1.05x. And now do the same thing that I've been doing with the previous problems. Go ahead and take the derivative of that new expression here with respect to t. I could combine my x values, but I'm just going to keep them separate, just so I don't have this ugly number over here with the 500 just subtracting 1.05. But if you wanted to combine them, you can. The derivative of p with respect to t would just turn into dp over dt equals the derivative of 500x is going to turn into 500 times dx over dt, just like it did earlier. Then plus, this one's going to be for x squared over 25. That would turn into 2x over 25, then times dx over dt again. Then I've got minus a constant, so that would go to 0, and then minus the 1.05x, which the derivative of that would just turn into dx over dt. And now if I go ahead and plug in the values that they wanted, my dp over dt is going to be equal to 500 times the dx over dt, so 250. Then plus 2 times the x value, 5,000, over 25, but then times 250. And then minus the 1.05 times the 250 once again. So if I type all of that in and just figure out the value, we'll finish up this problem. So 500 times 250 plus the 2 times 5,000 over 25 times 250, then minus the 1.05 times 250. That would come back as what looks like 22 or 224,737.5, and again dollars per week. So my two solutions for the last two problems were right there. Go ahead and circle those up. But as you can see, we probably could have just taken, since the rates at which I did the revenue and the cost, I actually could have taken this value here at 225,000 and just subtract the 262.5, and that could have gotten me that value a little bit faster. But just wanted to show you how the calculus part of this works. Is we just set up the expression and go ahead and find what the derivative with respect to t is, and then plug in the values. Notice we still get the same value when it's all said and done. Anyway, hopefully this has been helpful in getting you guys to be able to work through the homework assignment. But if you have questions, as always, just reach out. I appreciate you taking the time to watch the video, and we'll catch you next time.